Alright, so I guess all the way down to past Python, past all this stuff, evaluating and controlling technology. So there's a lot going on the internet, right? Some of it is not good. How can we hope to control the things that are bad, and at least think critically about some potential issues, because there are downsides, right? There are downsides to technology, as many upsides as there are. Some things are still bad, right? So how can we cope with them and think critically about them? That's the idea. So this is kind of old news now. Things have gotten much better with the recent advances in AI in the past year or so. But I think deepfake was like the first really scary thing, if we remember that. That's the idea of like using machine learning, artificial intelligence to take a video and then put somebody else's face into that video, even though they weren't there. Okay, so this is not uncommon. This was not uncommon in images before, because everybody used Photoshop, right? It was normal to like swap faces in Photoshop and stuff like that. But a couple of years ago, right? A video, we still think of a video as like very trustworthy. You record something, it's pretty hard to fake that, right? It used to be pretty good proof that somebody was somewhere doing something, like a security camera footage, stuff like that. It's used in trials. So deepfake allows us to take a video and swap seamlessly people's faces. And so the meme is like everybody puts Nicolas Cage into every video. So that's the fun version of deepfake, but it could get worse than that, right? And be used for unfortunate things. So it could be used for fraud, hoaxing, and for the memes as well. But have we heard about that before? Have we seen that happen? That is not too great. Any comments about that? A bit unfortunate. So I guess we can't trust videos too much anymore now, can we? That's too bad. Similarly, some very common information sources that we use are potentially untrustworthy. So Wikipedia, for example, this is why all of your English professors yell at you about citing it. People can change Wikipedia. That's one of the great, wonderful things about Wikipedia, right? People are adding new articles. It's always up to date pretty well, because people can change at like 3 a.m. the contents of a Wikipedia article. So you can add things. So the information that was there yesterday might not be there tomorrow. It might be changed. It might be added to. So like you got your little article. You may see some text added the next day if something new happens, right? So Wikipedia is the greatest source of information on one hand, but on the other hand, that is potentially a downside, right? Because anybody can modify Wikipedia articles. Somebody could edit that article and put silly things, bad information, and for less popular articles, that bad information can stay there for a while, can't it? Because not a lot of people are going to notice it. So normally, if people are just doing normal vandalism, Wikipedia is pretty good about just automatically discovering the problem and reverting the changes and doing all that. But sometimes they're more subtle, and humans need to look into it, right? So we could technically go right now, right, to the Wikipedia page for Clovis Community College and change the picture of the school to a picture of our cat. Okay, that's totally possible. There's always that edit button. So let's see how easy it might be. You don't even have to log in, right? Clovis Community College Wikipedia, and then it's boop, boop, edit. You just click that button. You can save changes. You don't want to do that though, right? That button right there is so easy to click, and it knows. Okay, so that's unfortunate, perhaps. Yeah, and I'm sure you've seen Wikipedia articles that are not complete. Everybody says citation needed, even though they're not getting rid of that information. It's not good enough yet, and so some potential downsides to Wikipedia. But does that mean we shouldn't use it? No. I don't think so. I think it's a good secondary source. It shouldn't be our primary source of information, but as long as you read all the articles that Wikipedia cites and get your information from primary sources, it's probably a good idea. Okay, so here's just a funny thing that I noticed while I was on Reddit one day last year. There's this Wikipedia article. Somebody linked to California grizzly bear for some weird reason, and just immediately once I got there, I noticed that there had been some vandalism done. Right, so that is kind of funny, and it just goes to show how easy it is for that to get in there, right? Somebody can click save, and then the next person that goes to that article can see the problem, right? And maybe they believe what they see if it's like some factual issues. Okay, so that's Wikipedia. Here's some cool ideas. This one might be from the book, I think. Computers are great as well for, like, if you're about to make something that's physical and large. Let's talk about car crash tests. Every corporation that makes cars, they do have to go through a car crash test, I think. So here's my best drawing of a bad car. And, like, they put a little dummy inside of that car, right? And then they, like, hurl it into a brick wall, something like that. Like, you have to do that when you make a car, I think. They have to know that it's going to, like, crumple in the right way and protect the people as much as possible. It costs a lot of money to make a car and wreck it, right? So why not simulate that car crash test? That would be fun if we could do that. And it is possible. People are doing that. So the issue with that, though, is, like, with every upside, there's a downside. If you're going to model cars inside of a computer, like do it all inside of my laptop or something, somehow do a million car crash tests on your laptop, you have to give up some information. You have to model physics. You have to say what it means for this exact type of metal to crumple in this way. What does the structure look like? You have to, like, talk about every little detail of every little material if you want that test to be more or less accurate, right? And so we do have a lot of physics equations that we trust, but we can't model every individual atom of that car, can we, inside of a computer? That would take way too much memory. It wouldn't work out. So we have to give up some information. We have to simplify our simulations. And so the question is it okay to do the simulations then? If it's not really that exact same car that's being simulated and crashing, is it still a good idea to do this? Yeah. So yeah, you can go both ways, talk about both sides, but one argument for simulating car crash tests is that, like, eventually the manufacturer has to do a real one, and so maybe if they do a bunch of simulated ones, they notice some very obvious errors first, and then they fix the car, and so the car will be better in the long run if they're going to do these tests anyway. Like, they'll iron out the kinks more easily with software and iterate more quickly over their car designs. So that's one argument. But a counter argument to that could totally be like, well, what if the simulation is wrong and it's saying the wrong thing and they're fixing the wrong problems, right? Maybe they could have found a safer design in the end if they really did just make a million cars and crash them all. A million different designs. So there's two sides to that, but it's a cool idea. Are any of us engineers in the room? No. Making engineering models yet? So that's kind of cool to think about. So I just have a bunch of little anecdotes for the rest of the day. I did press record, right? Let's go back to, like, cell phones and things like that. If you download an app from an app store, for example, if you have an Android phone, Google can delete apps that you have bought potentially and downloaded. They have the power to do all that, okay? And the goal, right, is that a good thing or a bad thing is the question for every slide. The goal for this idea of being able to delete apps, the reason they reserve that right is so that they can delete bad applications. You think of, like, an elderly person downloading a bad app and not knowing it. Google can then go, once they discover that was a bad app, they can remove it from everybody's device. And so that maybe is an upside for that. But there are also applications that maybe people want to use that Google still wants to get rid of. So the question is, should they have this right? Should they be allowed to do that kind of thing? Apple also has that ability. A little relevant idea from a little while ago, I think it was like a year ago, right? Apple took down Fortnite, that video game, on the App Store because they were like, I don't know if they put it back up yet. They might still be feuding about this. I'm behind the times on this article, but that app violated the rules of the App Store, in which, like, if you pay for, like, a subscription, Apple needs to take a cut of it or something like that through in-app purchases that Fortnite was offering, and Fortnite wanted their money and to not give it all to Apple. And so because of those rules, nobody could download Fortnite even if they bought it or they made those in-app purchases on a new phone that they got or something. So that is that's unfortunate, but totally that's one of those terms and conditions that we agree to, right? So yeah, there are some rules to be on an app store. From on the flip side, if you're a developer making apps, and this is one case of the developers not following those rules, and that allows Apple to come in, Google to come in and delete those apps from the store and potentially from users' phones. Okay, so that's an interesting example. Have we heard about that story? Maybe it's been a while, I think. But the ultimate irony. This is a fun one. Apparently, once upon a time, Amazon was they accidentally removed copies of 1984 from Kindles, which is excellent if you've read the book. So that kind of power, should it belong to an app store?
No.
Maybe, maybe not. All right. So yeah, this is to get us thinking. Let's see some other issues with technology that we need to think about. Forced upgrades are a thing these days. Like if you have a Windows computer, it keeps nagging you to update to Windows 11, and I have not done that yet. And even Windows 10, like the previous version of Windows, a lot of people were on Windows 8, which was, I guess, old, and Windows tried to update itself, and it forced people to go to Windows 10 out of their control. All right, and that might have messed up some of their programs that were only working on Windows 8 or whatever. So that asks the question then, do we even have control over what is on our computers? We just talked about our phones. What about our computers? And so should we allow corporations to force upgrades on us if we liked the old version? And again, there's arguments for and against that. So if you have old software on your computer, depending on the kind of software, it can be very easily exploited. It's been around for longer, and so people have found problems with it. They can make their way into and eventually use that exploit to get all of your financial information or something, follow you around on your computer. So I guess forcing an upgrade upon someone is good because all of those issues are going to be automatically fixed. But on the flip side, as usual, you as the consumer who bought this expensive product that you wanted to remain exactly like this, you've lost control over that thing that you potentially paid for. So that is maybe unfortunate. Any questions, comments about that? I don't think Windows 10 is forcing upgrades to Windows 11. They're just very vocal about it, right? Yeah. So I got a couple more slides for this deck of them, and then we'll come to some other ones. So I guess the last main topic that I want to talk about here is equity. So technology is great because it's the great unifier. We can all work remotely from wherever we live. We can get better jobs potentially. Technology is excellent in that regard, but it also comes with the cost, right? A lot of people maybe can't afford that technology that would really help them get out of any rut that they're in their lives, right? So a lot of people with low income, they maybe don't have the computer or the fast internet connection that could help them get a better job, things like that, improve their lives in some way, right? For example, these days, if you don't own a phone, you don't have a cell phone, you don't have an email address, a way to get access to all those things, then nobody's going to give you an interview because you need to put at least those things down on a resume, right? So that's unfortunate. We have to think about that as well for the people who don't have that. So especially important during the pandemic that may or may not be still continuing. So for example, back then, right, online classes are still common. And if you take an online math class, I assume they're not going to let you take a test that isn't proctored, right? They'll make you come to campus, or back during COVID, they made you use Proctorio or whatever that app was that people hated. So that's the thing. If you don't have a webcam, you can't take this online class. You can't better yourself and advance your knowledge. So that's unfortunate. And then one unfortunate but so easily solvable problem is that the people who are writing programs are often think of your standard developer, right? they are usually white and usually upper class, right? Because they're making a lot of money. And so programs, the testers of the programs are usually the developers a lot of the time. And so programs are getting to be tested only on white people. And so maybe if somebody even has access to that fancy technology, it might not work for them depending on their skin color. And here is a great example of that. Here's a fun tweet from this person from the pandemic, where like they were trying to take a test and they couldn't take the test because of the color of their skin, because they weren't testing this product, this little proctoring software, on everybody that they should have. Yeah, so that's a problem, very easily fixed. So yeah, when you guys all become fancy developers, make sure to test your software thoroughly. Okay? Any questions about any of that before I switch gears to a completely different topic? So yeah, I think we now are thinking more critically about the stuff that we're using, and that's important. All right, so where are my other slides? This one. All right, so there's some issues on the internet, right? And so let's talk about it. Where was I? This one. So I forced you to read about one of these, right? So there's a bunch of errors that have happened inside of computers, even though we use them every day, right? They're still not perfect. Things have gone wrong. Let's talk about them. How could we, as a society, keep using computers when they cause all these problems? Is that okay? Are they really helping us that much? I guess I'm biased as a computer science instructor, but this is important to think about. So let's talk about some examples here, and then I think that'll be it. Some more examples. These are of larger issues, things going wrong, things blowing up. So let's talk about that. So here is a rocket. This was a rocket called the Ariane 5. It was made back in the 90s by not NASA, but just North American Space Agency, right? But ESA. It's the European Space Agency, so they have rockets too. And they tried to launch this thing, this Ariane 5 rocket, maybe to launch some satellites or something, whatever rockets do. And it unfortunately, they launched it for the first time in the summer of '96, and it blasted off, and 37 seconds later, it self-destructed. There was some code in it that self-destructs if something goes wrong, and it thought something went wrong, and it blew itself up because it thought that was the best course of action. It was automated. So what was the issue with the Ariane 5 rocket? It was a bug in the software. Nothing was really wrong. It just thought something was wrong and blew itself up, and it was almost $500 million on fire. So that was a bit of a problem. Let's talk about the bug. What went wrong? This almost $500 million bug back in the 90s. What did it do? How? It's so easily fixable, so it's fun to talk about. Luckily, there's nobody on this rocket. This was completely unmanned, so that's good. Just money went down the drain. Mm-hmm. So what they did is they tried to use Ariane 4 code. This was the Ariane 5 rocket, so they've done this before successfully. They tried to reuse code from a previous rocket, and things didn't really work the same. So the main issue was they tried to take a 64-bit floating point number. Remember what a float is? Yes. The float type in Python, float. It stores things with decimal places, 3.14. And it holds a lot of space, like it could hold some big numbers in scientific notation, like 5 times 10 to the 50th power, stuff like that, with some amount of precision. So they tried to take a large float that takes up 64 bits, or what 64 bits are. That's just a big number that's made of ones and zeros, and there's 64 of them total. So they tried to take a number that was expressed using 64 binary digits, and they tried to shrink it down for, some space saving, some faster calculation purposes. They tried to shrink it down into a 16-bit integer, 16-bit int. We know the int type, right? It does not have decimal places. So maybe they rounded. I don't know exactly what went on. Integers can hold whole numbers, positive and negative, but no decimal places. And they can't get too large either, especially if there's only 16 bits of them. So you can imagine, I think you can calculate the biggest 16-bit int, I think. And It's not that big. It's not as big as a float could express. So 16 bits here. So they try to take all these ones and zeros and somehow make the same number with much fewer, 1/4 of those ones and zeros. Okay? And yeah, I hope that made sense. You know all those words. I think I hopefully explained them all in the right way. But that number, that special number that was the problem, it represented the horizontal velocity of the rocket. And so let me try and explain what that means. So like here's, I don't know, it's blasting off. Here's Europe, right? There's Italy, there's like the UK, blah, blah, blah. So here's the rocket. It's blasting off out into space. And the horizontal velocity, I assume, is like relative to Earth. So it's like how far, like it's going up in a certain amount at a certain speed. And it's also like veering off at a certain speed. And I think that's what horizontal velocity means here. And so that number that they were using for their calculations to be like, am I moving too close to Earth? I want to go straight up, stuff like that. Unfortunately, the number overflowed. And so what overflowing means is that you just didn't have enough bits to store the real value that it should have been holding. And so it instead, like if you add a bunch of ones, let me show you overflowing before I talk about the problem. Let's pretend that we're storing numbers with 4 bits. Let's say that we only have 4-bit numbers. So the smallest number is a bunch of zeros, the number 0, all the way to 4 ones. That's the biggest number that we could represent with 4 bits. What happens if we have 1111 already, and we try to add another 1 to that in binary? Well, 1 plus 1 is 2, that's 1 0. So here I am doing binary math. You have to carry everything. So 1 1 1, and then there's like one other 1 over here. This is a 0. But so the result is this. That's the final answer. But we only have 4-bit numbers in this example, so we just kind of get rid of that carry thing that made the real answer. And so do you see how a giant number, if you just add 1 to it, the biggest number, it becomes 0. It becomes very small. That's what overflow means. So a number that should have been large maybe became small. And there just wasn't enough room to store that converted value properly. And that's why it blew up. It thought it was moving too slowly, maybe. It thought it was like crash. It was going to crash, so it wanted to crash in the air instead. And so, yeah. This wasn't a problem. They reused the same code, and this code was not a problem on the old rocket, on the Ariane 4. Because back then they thought like the horizontal velocity of the rocket would never get to be that large so that it would overflow. But no, they made a faster rocket. Or they shot it off in a different way. And so that reuse seems very subtle. It caused the rocket to self-destruct. It thought there was a problem, and it cost a lot of money. So hopefully they learned from that. Any questions about that? It's just like, I think one line of code probably blew up a lot of millions of dollars. That's fun to think about. It happens. But we still trust software. We get it right eventually, hopefully. There's also issues with voting systems. This is a big thing about that the book talks about. So there are electronic voting systems in places. I don't think we have any in California, right? I think it's all paper because of these reasons. So back in the day, some electronic voting systems, and I'm sure this is still common in places, electronic voting systems, if the power goes out or if there's a bug in their software, like you can't vote anymore because the system crashed. That's so unfortunate, right? That's not good. We need to make sure that those are very, very stable. Also, a county that was using electronic voting, they lost about 4,000 votes because the memory of that voting machine that everybody was using was full. It just stopped counting, stopped adding. That's insane. That doesn't happen with paper, right? So a lot has to go on if we want correct software, right? So this is trying to motivate the idea of we need to write our software correctly for certain things like rockets and voting systems, right? I guess in Texas, apparently there is an error. They caught it, though, luckily. It generated 100,000 extra votes. That's quite a lot. That could change an election, can't it? That's not good. And then finally, another example is a bug caused, this is the most worst, this is the worst problem that you could possibly have. It caused some people some candidates to receive votes that were cast for other candidates. So like you press one button, it goes to the other guy. You press one button, it goes to the other guy. So that's horrible. And so I guess that's why California has picked paper still. But some countries, like Estonia, they vote online. They trust the system, and it works out for them. But yeah, the moral of the story is that some software should be correct, and it's very hard to make it correct. I think you know by now, you've written a lot of programs, right? It's not usually right the first time, or the second time, or the third time. You have to keep practicing and keep trying, and eventually it'll be right. But that's a bit of an issue. Any questions, comments about that idea before we get to the topic of your essay? All right, so yeah, let's talk about the Therac 25 now. It was a bit of a problem. So this was back in the 80s. It was a radiation therapy machine, right? It was controlled by a computer. That's why we're talking about it in this class. So it was an automated system, and it was used to like fire radiation at specific parts of somebody where there's cancerous growth, and it's supposed to make the cancer go away, hopefully, right? And so this machine, this Therac 25 machine, this is a high number. It wasn't the first one that they made. It was made in 82, this version, and there were problems with it most likely from the get-go. But the first accident happened in 1985, the first documented accident. And then they started realizing, oh no, we have to shut this down. So this is one of the worst bugs that we could talk about in this class, right? This is, there were some errors in both the design of the machine as well as the code that was being used. There was some reuse that shouldn't have been done. Again, the code ended up causing people to get 100 times the amount of radiation shot at them than they were supposed to get. And unfortunately, radiation therapy is kind of like fighting fire with fire, right? And so if you give too much, you can cause more cancer. And that's what happened. That's really bad. So yeah, a horrible, horrible issue with this code. And the previous versions of the machine, though, this is not the first one. I think the one before it was like the Therac 20 or something. The previous version of the machine had hardware systems in place to block that excess radiation. So even if the software messed up, it would be fine. But sadly, they took that away. Okay, so here's like what's it called? I think it's like a radiation beam. And what happened was there was a bug in the code from like the Therac 20 machine, I think it was called, that would cause this problem too. It would send out 100 times the amount of radiation when it shouldn't have. But there was a hardware lock in place on that machine. There's like a strip of wood or something that blocks enough radiation. And so it wasn't ever causing problems. It was fine because the hardware designers didn't trust the software designers, and they shouldn't have. So that was great. And so this worked out, and then they took this guy away. They took this little safety device away because the previous machine worked fine as far as they were concerned. And so they reused the same code, again, that controls this beam. And sadly, a bug caused it that same bug that existed before, caused it to shoot radiation, and it wasn't being stopped now. That was horrible, right? And I'm sure we have a lot to say about that. So here is a little debate that I want us to have now. So a lot of things we've seen some examples of things going wrong. Let's go to the written nice page, please. I'll clear it out.
Okay, then.
And then I want you to get into groups in just a second after I explain this and talk about the following. Here's the debate I want you to have. So when something goes wrong, right, in code, maybe it hurts somebody, maybe it blows up something very expensive. When something goes wrong, is it the programmer's fault when something bad happens and people maybe end up getting hurt? So that's your question. It's a very open-ended question. I'd like you to not pick a side this time. I'm not going to give you like even groups do this, odd groups do this. I'd like you to come up with one argument for each side, please, as a group. So give me one argument, yes, it is the programmer's fault, and here's why. Give me another argument saying, no, it's not the programmer's fault, and here's why. So think about it from both sides.
Are you in groups this time?
Yes, please get into groups with the people near you.
Okay.
And I'll give you a few minutes to think about this.
Are you ready? Do you want me to write it? I have to write it for you. You are a pretty girl, you know. So what do you think? Why do you think What do you know? I think so. Let's think. What if the programmer's fault when something bad happens? You can share my idea, and I'll share. Programmer's fault because they should have tested it first, right? They should have. They should have tested it first to make sure that it was tested properly, that it was safe, and to make sure tested was safe. Let's also see what else we can. Let's see what else we can write. In addition, they may not have programmed something right. Not only they should have tested it, but also needed to check. In fact, they could get, if they didn't, the programs were also killed the patient if it wasn't. Ending up in court. Why do you think it's a good thing? Why do you think it's not their fault? Although it may be their fault, may not. Although the programmers program people will be annoyed.
All right, a few more seconds. Get your answers in.
It may not be their fault. First of all, what'd you say again? It could be the machine's fault. Yeah, that's a good idea. Well, because the machine wasn't giving.
All right, that's my timer. Get those answers in. Let's take a look.
Okay, let's move in.
I'm interested in seeing how you countered your own argument. Let's take a look here. So yeah, it can be the programmer's fault. It is the programmer's fault because the code should be revised and tested to make sure that it's safe to use. Yeah, it's a good idea. That would have been a good thing. That should always be the case. We should be testing our code. But we are human, right? And so maybe we miss something. So computers are machines that can do wrong stuff, even if the programmer is precise and careful. So yeah, early CPUs, they could probably mess up a lot. But yeah, you can sometimes have hardware issues as well. That's valid. Yeah, these are great ideas. Yes, it's the programmer's fault. They should have tested it. Good. It should also not be the programmer's fault because, yeah, programming is complicated. Maybe it was a subtle issue, it was a hard mistake to see. There's a lot to keep track of as you're writing a large program, I think you can imagine. So yeah, this is great. Is responsible for designing and implementing software systems. They must bear a degree of responsibility, or at least the company, right? They're just like architects. That's a great thought. I like that. And then, yeah, sometimes it's hard to test things. So these are great arguments and counter arguments. I like to see it. So now let's see if there's anything that is different down here. Just code is hard to get right. This seems to be the right answer. Yeah. And then it should have been tested seems to be the other right answer. Yeah. Wasn't meant to hurt people. Exactly. So yeah, thank you guys for doing this. These are great thoughts. Any comments, questions now that we've seen everybody's responses? So, what do we think? There's a lot going on there. There's a lot of moving parts, right? So, there's so many questions. How do we assign blame? Especially because, and this is super common, maybe it didn't come up as you were thinking about it, but this is the norm these days. If you're writing large software, especially one that works on a medical device or a rocket, you have teams working. It's not just one programmer. You have teams of people working on all this software. Maybe hundreds of people, thousands of people at large companies, right? And they're all working on their own little piece. And they don't have the full story most of the time, right? They don't know the big picture. They don't know what's going on. They don't know exactly how their code's going to be used. They're just writing what their boss told them to write, yeah? And so I think that side of things, right? You know how easy it is to make a program that was supposed to do one thing but does a different thing. And so it's very easy to mess up. It's very easy to not fully understand what should be happening. And so that kind of takes away the blame, I think. And at the same time, maybe the company should be responsible. What they should be doing is testing their programs as much as humanly possible on every different possible use case of those programs. And you should also, for mission critical software, there's a topic called verification in computer science that sounds to humans like it's a synonym for testing, but it's a different thing. It's a bit more what's the word? It's a bit more precise. You want to if you verify something, that's a bit of a stronger guarantee than if you just tested it. Okay, so I'll try and explain both because they're not exactly the same, but testing makes sense to us as humans very easily. So let's write a test and a program, I think. So this is what we should be doing for all of our programs. It's the easiest way to catch bugs. It's what's going on most of the time. It's the way that software is being evaluated when you're writing it at a company. Testing is a very low effort thing that you can do, and it usually works well, assuming you wrote good tests. It's not going to catch every bug, but it'll catch a lot of them. The better the tests you write, though, the better it works. And sadly, a lot of programmers, they hate writing tests, and so sometimes companies hire programmers that specifically create tests. Other times, the programmers are dragged kicking and screaming into writing tests themselves, and sometimes that doesn't work out very well. So hopefully I can instill in all of you a desire to make tests. But here's an example test. You write some code, or maybe your buddy writes some code, your coworker writes code, and you treat that code as a box, a black box. Your code, somebody else's code. What you do is a test. All a test is it's you give the inputs that your code expects. My code takes 2 numbers, let's say, and it's supposed to spit out an answer. What you're supposed to do, what a test is, it's just hard code this input and figure out in your head what the code should have done. Okay, we should have seen 13 as the output. That's what should have happened. And then go and run the code on those exact inputs. Make sure you see that exact output. That's all a test is. It's with those inputs, try this input, make sure you see this output. Or try this next input, make sure you see another output. And if you saw a 33 instead of 13, now it's a problem. Something like that. Okay? So here's an idea. Example test. All the test is comparing what your code gives back to what you expected it to give back. It's very, very simple, right? If only people wanted to write more of these. So example test, like try input 42, and then just confirm. Take a look at the answer, confirm that the code gives back the answer for output as like 13. Confirm that the output is 13. Okay, so that's the idea. Let's write a test just for fun. Let's do it in Scratch though, because I haven't taught you if statements in Python. So we need to be able to test things. So I guess I lied about we'd never talk about Scratch again. This is secretly the last time we'll ever talk about Scratch, I think. So let's make a program and a test for that program. I'll show you how to do it. It's not too horrible. Let's make our own block. Remember that? I showed you how to do that at the very last Scratch lecture. Let's make our own block that multiplies all the numbers from 1 to some value where you can input the value. I think we didn't have time to show that kind of block, but like you can put whatever you want here and it'll work its way up to that. And so we're going to make this block, and then the goal is to make a bunch of tests. All right, so let's make the block first, and then we'll make a bunch of tests. So the idea is, let's set this up, I guess. Let's set it up first. Let's go to scratch.mit.edu again. How are we doing on time? Not too horrible. So there's that. And let's go down to my blocks, and we'll make a block. I'll say multiply, if I can spell multiply, the numbers from 1 to, and then I'll add a little input, add an input. And then I'll call this input like n or something. There. And so you can make your own block that takes a piece, and it runs differently depending on what you put in there. It's kind of cool. So that's the block that I'll make. I'll hit OK. And so now I can use it a bunch of places. Multiply all the numbers from 1 to, I don't know, 1 to 5, 1 to 4, whatever. I could also multiply all the numbers from 1 to 3. But right now this code does nothing. Like this block, we have to say what it means to run this block where 4 is this thing. We have to say what it means to run this block where 3 is this thing. And so that's what the definition block is all about. What it means to multiply the numbers from 1 to, and then call the thing that you were given n. It makes its own little definition level variable for you to use there. And so let me show you how you would do this, right? So we'll set up a variable called maybe like product. And it starts at 1 because we're going to multiply a bunch of numbers into it. We don't want to like start at 0 because then it will never become anything other than 0. And then like we're given an n value, like maybe n was 4. That's like its own little variable. And what we want to do is we want to take this 4 and multiply it into product. And then we want to multiply also 3 and 2 and 1 into product as well. Okay? So like decrement the 4 and make it 3. Now multiply the 3 into product, make it 12. Decrement n. That's going to be the loop that we're going to do. Yeah? Take the 2, multiply it into product. Now it's 24. Now make it 1. I guess you can multiply the 1 into 24 one last time, even though it doesn't change. Still 24. Now decrement n, make it 0. And this is where our loop is going to stop when n is 0. All right? And then we'll have an actual product, and we can like have the Scratch cat shout out the answer. So let's do that and see if it is correct. So as I run all of this, I'm going to need a variable. So multiply all the numbers from 1 to something called n. I'm going to need a product variable, so I'll make a product variable. And then I'm also going to need to, sadly, this variable that's specific to the block is not changeable. So maybe I can make my own orange n variable. That might work. Or maybe I should call this something else. I don't know. I'll call it like num. So n is what we get, but we can't modify it like we need to. So maybe I'll call this num over here. Boop. So here are the two values. And so once like we're given a value, multiply the numbers from 1 to 4, the code jumps up here and it goes to this block and n is set to 4. And then when we say it this way, multiply the numbers from 1 to 3, the code jumps up to here and starts running all the blocks below where and it has n set to 3 in that case, because that's what was passed along to the block. So, all right, the start of this should be set product to 1. Set product to 1. Initialize our variables once we get here, and then set the number variable to whatever n is, because now I can change num. It's an orange variable. That's fine. That's changeable. Okay? And now the loop is until, repeat until num is 0, this idea of like multiplying num into product, and decrementing num. Okay? So it's a good programming lesson once more, I guess. So repeat until num is equal to 0, something like that. Oh, sorry, not or, but equals to. Repeat until num is equal to 0, because we're going to be decrementing it every time. Multiply this number in, decrement it. Multiply this number in, the product, decrement it. And then the thing that we're repeating is always take the number in num, multiply it into product, change product based on it, and then decrement num to be the next number in the next round of the loop that I want to multiply into. So set product to be product times num. So that I get my multiplication block out, or my multiplication thing. Set product to be product times num. So there's that one. And then also decrement num. So change num by, I guess, -1. That works. And then after this is all done, product should have the right answer, right? Product should have the right answer at the end of this loop once we break out and num is 0. Then I guess we should just shout out the answer. That's I guess the only thing the Scratch Cat can do, because we have to give it a block to run. So say product for 2 seconds, I guess, because that's where the answer is going to be. So what is 4 times 3 times 2 times 1? That's 12 times 2, which is 24, right? So I run this block. Hey, it works. We get 24. And you can watch it work if you want to add a wait block. That's totally all possible. Wait 1 second, blah, blah, blah. Multiply all the numbers from 1 to 4. You can watch it change the values, putting it into num, putting it into product, decrementing num. 0 now, 24, cool. Multiply the numbers from 1 to 3. It's like, okay, that goes all the way to 6. That's correct. And so these could become tests now, okay? So let's write some tests for this program. We should, as far as Scratch is concerned, you just make a block and say, this is what it should have been. This is what it should have been. So we can have a test, multiplying all the numbers from 1 to 4. That better give back what? That better give back 24. Multiplying all the numbers from 1 to 2 should give back 2 times 1, so 2. That's another test. Multiplying all the numbers from 1 to 1, that should give back 1. That's kind of an interesting test, because it's going to run the loop only 1 time. It's kind of interesting. So these could be valid tests. So multiply all the numbers from 1 to 4 and be should print, I don't know, 24. Multiply all the numbers from 1 to 2, should print 2. And these can be our tests, right? Multiply all the numbers from 1 to 1, this should print just 1, yeah? And so you can run them all and make sure it works. That one was 2. This one is going to work. It's just going to be 1. 1 was the answer. These 3 are working. These tests are working. But there are some things. There is a potential issue with this code. We want to test what are called corner cases. Right? That's where things are doing the loop runs 1 time only, or 0 times. We skip the whole thing. Stuff like that, where you give bad input. You got to think about those kinds of things. Those are called corner cases. And that's where the program is about to do something different, stuff like that. So some good corner cases are 2, 1, and multiply all the numbers from 1 to 0. That could be an interesting case. How do you multiply all the numbers from 1 to 0? Does that even make sense? Are there any numbers between 1 and 0? So you have to that's going to force you to maybe change your program. What does this even give back right now? It gives back an answer of 1. Is that even correct? 1 to 0 in that order? Should it print 1? Maybe this should be an error. And so you see how making a test and thinking about what should happen maybe informs the way that you write your program, and maybe you have to change it now. Isn't that interesting? That's a possibility. But yeah, you want to come up with a bunch of these cases, corner cases, that mess with things. You want to compare. It's always compare what you got. So you see the output, and you compare it with what you expected to see. All right? So that's the idea. So test some corner cases, test some very incorrect cases, give a -42 value, multiply all the numbers from 1 to -42, and then test some normal numbers for the general case. I think 4 and 2 are fine. Maybe 8 as well. But it's always compare what you got with what you expected, And so maybe we need to change the 0 case. We'll get to that. One more. This one should totally be an error message. Exclamation point. Multiply all the numbers from 1 to negative 42. What does this even do right now? Well, it's multiplying num into product. And it's going to keep doing that. You see how product is getting giant? It's going to keep doing that until num is 0. But num is negative, and we're subtracting from it. Will it ever become 0? So this is an infinite loop right now. This is a problem. So if you give bad input, now your answer is never going to be finished. It's never going to compute. That's not fun. So you see how making tests is telling us, okay, we need to change our program. We need to make it more error-proof. So that's going to help us here. So maybe before we ever run this loop, we should check and see if, like, hey, is n at least 1? If it is less than 1, I think we have a problem and we should probably bail out. All right? So add a little if here. That's like if, and we noticed we needed that for a couple of our tests, right? If num is less than 1, like 1 to 1 makes sense, 1 to 2 makes sense, but 1 to 0, that's the first time it stops making sense. So like if number is 0 or negative 1 or anything smaller than 1, then this is a problem. This is an incorrect use of our block, okay? And we should shout out about it, like invalid input, something like that. Try again. And we shouldn't allow this to continue. We should not allow this code down here to continue. And so one way to do it would be like have an if else and only do the repeat until in the else, or you can add a stop block here. I think that's in control, right? Stop. Do not continue. So that's one way to do it. And so now, once we have that, these corner cases should be better. It's like invalid input. Invalid input. Great. And then we need to make sure the other ones still work. Like it still gets to after the if into the loop and does the right thing for the rest of these. Like 1 to 1, does that still give back 1 as we expected? Yeah. 1 to 2, does that still give back 2 as we expected? Yeah. What about 1 to 4? That should print 24. Is it going to do it still? Yes. So that's a much more correct example, and making test cases caused us to think about the correctness and maybe change our code. Any questions about that? So that's one common way to make your code better, is to make tests for it. And that's that's probably the most common thing in industry, I would say. That's the most common way to make sure things are correct. Yeah. And so I think that is where I want to stop for today. If we don't have any questions, let's see if there's anything to release. Nope. So it was just the lecture today. The rest of the time is all yours to work on stuff that's out and to ask lots of questions.